Olá, gente. Bem-vindos. Desculpa o pequeno transtorno. Bem-vindos ao último seminário de semestre. Pode ser o último seminário na era de Zoom, ninguém sabe. Hoje vamos ter uma coisa, concluir o semestre com uma coisa um pouco diferente, mas também extremamente relevante a nós. E vamos falar de fusão nuclear, que não é física de leis fundamentais da natureza, mas pode resolver definitivamente o problema da energia e mudar todas as nossas vidas, se dá certo. O Dr. Nick Walkden, temos a honra de ter o Dr. Nick Walkden, que ele fez graduação em física na Universidade de Bath, e depois o doutorado na Universidade de York, na Inglaterra, e agora trabalha na Autoridade para a Energia Atômica em inglês. Ele é experto das tentativas de fazer fusão, produzir energia com a fusão nuclear. Alguns de vocês podem ter lido que recentemente teve um progresso significativo nisso, então ele vai introduzir os desafios disso e as promessas. Nick, thank you very much for coming and speaking to us. Please, you have the floor.
Brilliant, thank you. And once again, I'm so sorry to keep you all waiting. I hope that this is worth the wait, and it shouldn't take me. It shouldn't take me 50 minutes to go through my slides, so there should still be time for you to ask me some questions at the end. My training is in plasma physics, so I've got a degree in a PhD in plasma physics. I worked on various experiments, mainly around Europe, in UK, in Germany, in Switzerland. And in the last couple of years, last 2 years, I've been working with government and to look at more strategy and policy related to fusion, as well as fusion research. So I've got quite a wide-ranging background. This seminar is really aimed to give you a very broad overview of fusion science and technology, what we're doing in the UK, but also a little bit about what's going on around the world as well. And then I'll delve into a little bit more detail in a couple of areas where plasma physics is more important, but it's not going to be a hugely detailed talk. I'm more than happy to come back and give a much more detailed talk in any subject in the future. But I thought it would be better to give you a good, very broad overview for now, and then let you decide if you'd like to see more. If I can make my slides work. So this is me. This is a pretty awful picture of me. The point I want to make is that I am currently 32 years old. So I'm 32 years old, which means that in 2050, I will look something like this. I see something in the chat. Okay, brilliant. It's not for me. So in 2050, I will look something like this. Why am I showing you this? Well, I'm showing you this because when 2050 comes to pass, I will still be working. I won't have retired yet. I will spend all of my adult retirement life in the net zero era. After we hit 2050, after the world has hopefully gone to net zero in our energy system. This is my son. So I mentioned before, I've got a 1-year-old son. He's 14 months old now. He will spend the majority, most of his life after 2050. So he'll be about 30 when 2050 comes around. He'll spend most of his life in the net zero era. He'll be 80 when the end of the century comes around. So he will live in the 2100s. I'm showing you this because it means that all of the stuff we hear about climate change, net zero, reducing carbon, it's all very big, it's all very difficult to comprehend, but it has real impact on me, on you, on our children, everything. Everything we do is about making sure that by 2050, by 2100, we have an energy system that allows our future generations to keep going with a high quality of life. So what might the energy landscape look like in 2100? This is a figure from the International Energy Agency. It was from 2019. You don't need to worry too much about the details here, but what I want to show you is that this figure predicts, that our energy usage will grow, right? So we're going to use more energy in 2040 than we do today. We'll use more energy in 2100 than we do in 2040 or 2050. It also predicts that at the present rate at which we do things, our fossil fuel dependency will stay about the same, but it won't reduce. It won't reduce by 2040. That's what this prediction from 2019 was saying. And this is a big problem because, of course, what we really want to do is have something that looks like this, where this big chunk of fossil fuel dependence tails off so that we have an entire energy portfolio that doesn't depend on carbon. Right. So that's quite a big thing to do. I'm going to put this into a bit of context for you, and I warn you now, it's quite scary. So in 2018, we burnt 11 billion tons of oil, or the equivalent of 11 billion tons of oil in fossil fuels around the world. There are about 11,000 days between now and 2050. So that means that we need to get rid of 1 million tons of oil equivalent every single day between now and 2050 if we were to achieve zero carbon. 1 million tons of oil every day. That's absolutely insane. It's the same as building a brand new fission power plant, a brand new nuclear power plant every single day between now and 2050. So it's just an enormous task that's ahead of us. The reason I show you this is because I think it's completely unrealistic to assume that we can do this without some new technologies, without some new ways of boosting our dependence on, or removing our dependence on carbon-based fuel sources. Now, of course, we expect renewables, this big green block, to play a big role, right? By the time we get to 2100, we'd hope that renewables would play a big role, but they can't play the only role, because what happens if the sun goes out? What happens if the wind stops blowing? You have much less renewable energy in winter than you do in summer. So they can't play the only role. There has to be something underneath renewables that allows you to get to this point. And what I'll say today is about fusion energy as a potential to be within this something. So there are lots of benefits of fusion. It's low carbon. So the fusion process itself produces zero carbon, and it doesn't use a lot of land. So it doesn't have a lot of carbon to build the machines. It's inherently safe. So it doesn't produce any sort of meltdown scenario. It basically turns off as soon as you shut the machine off. So it's very safe and very controllable. It's very reliable. So you can have it on when you need it. You can turn it off when you don't need it, in theory. And it's sustainable. So the fuels that we need for fusion, you can get from seawater. You can get deuterium from seawater, which is just heavy hydrogen. So one proton, one neutron. And you can get lithium from seawater. And if you hit lithium with a neutron, you breed tritium, which is the other fuel we need for fusion, which I'll talk about in a minute. And fusion is the most power dense process we have available to us on Earth. So it produces an awful lot of energy for very little land use. So there are lots of really strong benefits of fusion, lots of reasons why we want fusion to be within our energy portfolio. So what might that look like? Well, let's say in 2100, and I've put ish here. So that means that this might be 2100, this might be 2080, this might be 2120, who knows? But around about the end of the century, we expect the total amount of energy that the world is going to use to be about 20 terawatts. So let's say, what happens if we want fusion to be about 10% of that? So 2 terawatts of fusion energy. Well, that means that by the end of the century, we need to have between hundreds and thousands of fusion power plants putting energy onto the grid by the end of the century. So that means if we say a fusion power plant has a lifetime of, say, 40 years, we need to be building tens of new fusion power plants every year for 40 years from about 2060. So that means that by the time we get to 2060, we have to have a reasonably mature commercial market for fusion. So we have to have lots of different designs on the market, and we need to be able to produce sort of several tens of these designs. So that means, if you take this back even more, it means that we need prototypes for fusion power plants to start coming online somewhere around about the middle of this century. So between sort of 2040 and 2050, we need fusion power plant prototypes to start coming online in order to achieve what we want to achieve by the end of the century. So what does fusion look like as an energy source? Where does fusion energy come from? The best reaction for fusion is between two isotopes of hydrogen: deuterium, this D, which is 1 proton and 1 neutron, and tritium, this T, which is 1 proton, 2 neutrons. Heat them, put enough energy in so that they overcome the Coulomb barrier, and fusion occurs, and it produces helium and a neutron. And of course, if you take E equals mc squared, there's a deficit in mass across this reaction. So there's less mass on this side than on this side. It's not very much. It's only about 2% of the mass of a proton, but that's quite a lot of energy. So it's about, in this reaction, you produce 17.6 MeV of energy output. 14.1 of that is contained in this neutron. And this is the energy that we harness for electricity generation. This flies out of the machine, hits a water blanket or something around the edge of the machine, heats that up, produces steam, drives a steam turbine, produces electricity. But there's also 3.5 MeV of energy left in this helium or alpha particle. And that energy goes back into heating the plasma, heating the deuterium and tritium, so that more fusion can occur, and it starts to become self-heating. What that means is that 1 gram of DT fuel is enough energy potential for a single person for around 20 years, which is the same as about 20 tons of coal. So the potential of fusion is enormous. We just have to harness it. So how do we do fusion on Earth? There's a very famous condition that you may or may not have heard of called the Lawson criterion, which you can derive this by balancing the amount of power lost by radiation from the plasma with the amount of power produced by a self-sustaining fusion burn, so a self-sustaining fusion reaction. When you do that, you arrive at this criterion, which says that the amount of density, the electron density, well, actually, I think this is the ion density, times by the electron temperature, times by something called the energy confinement time, which is how long do you keep all of the heat inside the plasma for, has to be greater than this big number. In fusion, this doesn't need to be a huge amount. So this is about 2 grams of deuterium or 2 grams of tritium, but the temperatures are significant. So we need to go to hotter than the sun. The sun burns at about 10 kilo electron volts. We need to get up to about 100, 150, 200 kilo electron volts before we get a decent amount of fusion being produced. And we have to let it sit there. We have to control it for a certain amount of time so that we get enough fusion energy. Now, this is a condition that doesn't depend on the way that you do fusion. So it doesn't depend on your fusion technology. And you can see that you could achieve this in a few different ways, right? You could achieve this by making this thing really big. So if you make the density of the plasma really, really high, then you can do fusion just because you've compressed a piece of fuel so much that you've got a small amount of fuel with so much fusion fuel in it that you produce a lot of fusion. This is exactly what inertially confined fusion is. So inertially confined fusion is called inertially confined fusion because the only thing that's really holding it in place is its own inertia. You fire lasers at it, and those lasers cause the fuel to implode on itself. And when the fuel implodes to very high densities, it forms a hot spot, and in that hot spot, you start to produce fusion. The National Ignition Facility, which is a facility you might have heard of in Lawrence Livermore National Labs in America, is exactly one of these. So this is what NIF does. And you might have heard some recent results that came out of NIF, which said that they've managed to achieve more energy out than they put in. What they've actually managed to do is the hot spot at the center of the fuel has produced more energy out than the amount of energy that got put into that hot spot, which is about 1 megajoule of energy. So it's quite a lot, It's a lot of energy, but it took about 100 megajoules of energy to achieve that. So it hasn't produced anywhere near net electricity, but it's still, from a plasma physics point of view, it's still a really, really great result because they've achieved more energy out of the plasma than they put into the plasma. So very exciting. You can do it a different way. So what happens if instead you say, well, I'll have a reasonably low density, but I'm going to keep my fuel there for a long time so that I get more fusion reactions just by having the fuel there for a longer period of time. And that's what magnetic confinement fusion focuses on. And that's what I'll talk about mostly for the rest of this talk. You can put that on a graph. So if we take two of these parameters, if we take the density and the time, and we fix the temperature, if we take the temperature as being 150 kilo electron volts, then you can plot a graph and you can put these different experiments on the same axis. So all of these are the magnetic confinement experiments. You see they cluster down in this corner here, where they last for longer times, but at low densities. Or you can have inertial confinement fusion, which is up here, which is at high densities, but for nanoseconds. And actually, there are a range of other concepts that I haven't put on this graph that fall somewhere in between these two. And you can see actually, NIF has done pretty well if you count just the energy into the hotspot of the fuel. Down in magnetic confinement fusion, we haven't quite got there yet. So JET is in existence, and I'll talk to you a bit about that in a minute. And JET is nearly at ignition conditions, nearly at this line, but not quite there yet. But ITER, which is the next stage in fusion development, will sit above this line. And ITER really will produce about as much energy as it takes to power the whole plant. So it really will produce net energy. And it'll produce 10 times the power out that you put into the fuel. So it's a very exciting experiment. But it's really, really hard. Fusion is just really hard to do. I give a lot of talks to public audiences, non-academic audiences. And what I always say to them is that fusion really is essentially breaking the laws of nature. So nature tells us how big a fusion reactor should be. It's the size of the sun, right? Because the sun is nature's fusion power plant. The sun takes an awfully long time to produce power. It's not very efficient. So we need to be hotter than the sun, but we need to have all of this heat confined in a volume which is much, much, much smaller than the sun, about the same as a few houses. And this creates a really intense source of neutron irradiation, the most intense source of neutron irradiation that the world will ever have seen. The first time a fusion power plant turns on, it'll be more intense than anything the world has ever produced in terms of neutron irradiation before. So it really is really, really hard. We really are bending the laws of nature to try and get this thing to work on Earth. So the leading concept for fusion is something called the Tokamak. This is the most mature design that we have in the world at the moment, and it's the one that we, at our lab in UKEA, it's the one that we focus on. The Tokamak, a Tokamak basically means three things. It means toroidal chamber, these two words, toroidal chamber with magnetic coils, and that's essentially what it is. So there are three main features. At the core, you've of course got a plasma. So you've got deuterium and tritium, which you've superheated and you form the plasma. You've got magnetic coils around the plasma, and that's to keep the plasma in place because, of course, magnetized plasmas can be kept in place just by putting a magnetic field through them. And you've got a vacuum vessel because anything that goes into the plasma that is not a plasma constituent, a piece of the fuel, will radiate heat away. And heat is energy, energy is fusion. One day, hopefully, fusion is money, so you can't have that. And there are a lot of challenges, right? It's not just the plasma that's hard. So yes, we have to control a fuel that's hotter than the center of the sun. That's plasma physics. We have to make sure that we can keep that fuel, that plasma steady and stable for as long as we need it to. We also have to be able to extract the heat that we can't use to make electricity without damaging components. And these things are producing a lot of heat. So this is a big challenge. We have to be able to extract that heat without damaging the machine so that it can keep running. We have to design the machine out of materials that can withstand the most intense source of neutrons on Earth. And neutrons do a lot of damage to materials. So this is a really difficult thing to do. We have to be able to test these big scale components, you know, meter scale components in conditions that are at least reasonably similar to those in a fusion power plant. And that's not an easy thing to do, because how do you replicate these conditions without actually building a fusion power plant? It's very hard to do. We have to be able to produce and store the fuels we need. So deuterium is common in seawater, so we don't need to worry about deuterium. But tritium is radioactive. It's got a half-life of about 12.7 years, so it doesn't occur in nature. It only occurs if you make it. The way we're going to make it is we're going to take lithium and bombard lithium with a neutron, and that produces tritium. But it's radioactive hydrogen, so it gets all over the place. It gets in all metals, all places you don't want it to get. So you have to be able to not just produce it, but store it and control it in a way that's safe. Very hard to do. If you can do all of this, you will still have to repair your plant from time to time. And you don't want to send humans in to do that, because we've got soft and squishy bodies. So you send robots in to do it instead. And you have to be able to build fleets, thousands and thousands of robots that can operate and repair these things all remotely. And finally, if you can do all of these 6 things today, you still have to figure out how you do them in a fusion power plant without actually having a fusion power plant to test them in. And the only way you can do that is with really clever advanced simulations. So there's a lot of challenges that we have to solve in order to get fusion on the grid. Now, we're working on all of these, right? The global community is working on all of these challenges, but they're not insubstantial, right? There's a substantial chance that one of these will prove insurmountable. But we hope that that won't be the case, and we're working very, very hard to make sure that they're not. I'm going to focus on 2 of these in the rest of this talk, because these 2 are the 2 that most concern plasma physics, so I thought they'd be most of interest to you. And I'll tell you a little bit about some of the experiments we're doing today that are helping to address these. So how do you control a burning plasma? Well, you do an experiment to do it. And the machine that you can see here is JET. JET is called the Joint European Torus, and it's housed at our lab in Culham, but it's the biggest fusion experiment in the world. It's the only fusion experiment in the world that can run with deuterium and tritium fuel. And it is unique in that it is what's preparing us for the next stage in fusion, because it's able to test out the physics of how you control a burning plasma with deuterium and tritium fuel. It's very pretty. So this is I always like this diagram because it's all shiny and made of metal inside. It's not just made of metal to be shiny though. The materials that are made inside JET are an exact replica of the materials that will be used in the next stage of fusion device, which is called ITER. ITER is being built in the south of France at the moment, and it will prove that fusion can produce energy. And JET is the only training ground that we have in the world at the moment to prepare for ITER. I thought I'd show you what a plasma actually looks like in JET. So this is one of our pulses. This was back in, I think, probably about 2014, 2015. Now, what I really like about this pulse is, so it's starting to heat up now. And you can tell it's heating up because you can start seeing all of the radiation around the edge. What you can also see, excuse me, in this camera image are all of these speckles. If I go back a bit, you can see a lot of speckles. These dead pixels will appear in the camera. Now, this is not the camera going wrong. These are actually fusion-born neutrons. So neutrons born out of fusion, coming out of the machine, hitting the camera and causing the pixels to deaden. So you can actually see fusion happening in JET. So we can do fusion in JET reasonably reliably, which is very exciting indeed. And JET holds the record for fusion energy produced, or fusion power produced. In 1997, JET produced 16 megawatts of fusion power. So that's a huge amount of fusion power. That's about the same as a small field of wind turbines, right? Each wind turbine produces a wind turbine produces between 1 and 2 megawatts. So this is about the same as 8 wind turbines. So it's quite a lot of energy. It's not break even. So it isn't producing as much energy out as you put in, but it's getting close. This was in 1997. To put this into context for you with the NIF result, the result from Livermore, on the same basis as this, so this is total energy in to total energy out, on the same basis as this, NIF produced about 0.01 megawatts. So, or about 0.01%. So this is doing significantly better than NIF in this in the way that this is measured. So this is a big achievement, but actually probably the bigger achievement was this line down here, where it's not producing as much power, but it's producing that power steadily. Because you wouldn't, of course, you wouldn't want to run a power plant like this. You'd only get power for a blip of a second and then it would turn off. You want to run a power plant like this, where you're getting steady, sustained power. Now, JET will soon run, or JET is right now running experiments again after 20 years to try and do better than this. And what it's trying to do is two things. So this black line here, this is essentially the result that we got back in 1997. So you get, you can just take neutron rate is number of neutrons per second, multiply this by 14.1 MeV and you get power. So this neutron rate here for a blip of a second is what extrapolates to 65% of the power out that we put in. So that's the record. And you can see that as you get longer in time, so as you hold the thing for longer in time, you reduce the amount of power you can produce because it's harder to keep it there. What we've done in the last couple of years, not running in DT, just running in deuterium fuel, is we've shown that we can increase this duration and we can increase the yield of fusion that we're getting at these long times. And what we really want to do is do that even more. So we want to get this red line here all the way up to here, so that we've proven that we can operate JET at peak performance for as long as we need to. And if we can do that, then we've done everything we can from JET, and we've really done a great job of preparing ourselves for the next generation of fusion power plants that are going to come. And this is happening right now. So these experiments are ongoing. I'm not allowed to tell you how well it's doing, but it's doing very well. And you should hear more about these experiments in January. So please keep your ears open. Look at the newscasts, look at Nature, that sort of thing for these results in January. But the challenge is keeping the plasma in place. You're all physicists. Some of you have an idea of how plasmas work. Plasmas don't like to be kept in place. They have instabilities. So you try and keep a plasma in a nice donut shape and it kinks itself out. It causes an instability, hits a wall and dies away. They have turbulence. So all of these wispy things you can see here, this is turbulence in a plasma, in a tokamak. And turbulence takes the hot stuff at the center and mixes it with the cold stuff at the edge. So you get less heat in the middle of your plasma. And if things go really wrong, you have something called a disruption, where everything goes wrong and the whole plasma hits the wall and dies away. So you have to be able to control all of these different aspects of plasma physics in order to be able to get a plasma that runs for 5 seconds, 10 seconds, 100 seconds. And it's not easy to do. So that's the challenge. Oh, excuse me. So what's next? So today we have JET. JET produces 16.1 megawatts of fusion power, and it's a volume of about 90 meters cubed. From 2026 onwards, ITER, the next stage in fusion power plant development, comes online in the south of France. It's about 10 times the volume of JET, and it's about 30 times the power produced. And ITER is targeting a power factor, an output factor of about 10 times the power that we put into the plasma. And ITER is the stepping stone before we get to fusion power plants, which should produce between 1 and 2 gigawatts of power in volumes a little bit bigger than ITER, producing between 15 and 40 times the power out. So ITER really is this critical stepping stone before we get to fusion power plants. And it's 80% ready for operations. So it's being built in the south of France. This is what it looks like. It's huge. We expect it to be completed in 2026. It's a collaboration of 7 member states, so China, the European Union, India, Japan, Korea, Russia, and America. About 50% of the world's population is represented here in ITER. About 90% of the world's economy is represented here in ITER. And ITER will be the proof of principle. So ITER will prove that you can get more power out than you put in. And that's huge. That's game-changing fusion when that happens. We expect it to achieve this in around about 2035. So it's a little while off yet, but it's being built. It's 80% complete. And I just want to show you a picture to put it into some context how big this machine is. This is the vacuum vessel of ITER. This is one of the segments of the vacuum vessel for ITER, and these are the people that are installing it. The engineering challenge here is just utterly enormous. These vacuum vessels are 8 meters across. They're something like 14 meters tall. They weigh hundreds of tons. They have to be installed to sub-millimeter precision, right? Sub-millimeter precision. And they're doing it. They're actually achieving these feats. So it's just a monumental feat of engineering. Regardless of the science it produces, it will produce so much knowledge in engineering and fusion power plant design that it will already be worth it even before it comes online. So it's a really exciting project. So you could say you've got a plasma that's burning, you've got it working, you still have to deal with excess heat somewhere. And I've tried to put that into some context for you here. So say you've got a fusion plasma that's burning and it's producing 20 times the power out that you put in. Let's put some numbers to that. So we're going to heat the plasma with about 100 megawatts of heating power. We're going to produce about 500 megawatts of alpha particle heating from the fusion process. Now let's assume that we can cool, a lot of that will come away as radiation. We'll produce a lot of radiation, about 450 megawatts of that as radiation. You still have 150 megawatts of power, so more power coming out of the machine that you can't use to create electricity, that you have to deposit onto material surfaces. You've got more power coming out than you even put into the machine. So what do you do with this? Well, of course, we all know that that plasmas are tied to magnetic field lines because of the Lorentz force, so they can orbit around magnetic field lines, they can move along magnetic field lines. So if you curve a magnetic field line, then particles can orbit around that magnetic field line. Essentially, if you take a magnetic field line and you shape it, then heat and particles will follow that magnetic field line. So how do we create a tokamak that can deal with this sort of heat? Well, we start by creating a core plasma and running a current through that plasma. We run a current through that plasma and that creates a magnetic field that goes around in this direction here. So now you've got two magnetic fields. You've got one that's going into the page. You've got one that's going around in this direction. They loop, the one that's going into the page loops back round in the donut, and you've got a helix. So all of your particles, all of your heat follows a helix. Now let's put a second current down below some material down here and run a current through that coil. You've got a second magnetic field here that interacts with the first, and when you add them together, you get a point in space where there is zero magnetic field going in this direction, and that creates something called an X point. Now within this surface here, all of your plasma is contained, right? So it stays there, it doesn't escape, it just keeps looping around and around and around and around here. But outside of this surface, your plasma is no longer contained because it comes out here, it moves along a magnetic field line, and eventually it hits a material surface. So now we've managed to isolate this material surface from the core plasma. So that's a good thing. And essentially the way heat works is you generate a lot of heat in the core. You have a lot of heat moves along magnetic field lines, but a small amount of it can move across magnetic field lines in drifts or turbulence or things like that. So it moves out of the hot core, it moves across this surface, and eventually then it gets swept away as it moves very rapidly down and hits material surfaces down here. Because this is so rapid, it can't go very far, right? It doesn't go very far across this surface before it's swept away. So the amount of space that it actually takes up on this surface is very, very small, which means that it's depositing a huge amount of power in a very, very small layer, which is very, very dangerous. It means it's very easy to melt stuff. It's very easy to damage things. Today, in our experiments today, we are down in this sort of region here, about 10 megawatts per meter squared of power put onto surfaces, which is about the same as a car engine, a diesel combustion engine, so it's fine. In between here, we can get up to about the same sort of heats as a space shuttle on re-entry, which survives, but the way it survives is the armor it uses ablates itself, it destroys itself to survive. So really, we'd prefer not to be in this region because we want our machine to just survive and operate steadily. If we get up here, we're talking about welders, arc welders. These things are fundamentally designed to destroy the surface that they are impacting. So we really don't want to be up here for a fusion power plant. But the problem is we just don't know where we're going to be. We're producing so much power and we have so little understanding of the physics of how that's going to be deposited on material surfaces that we just don't know where we're going to sit. So we need to do a lot of work to come up with solutions that take this all the way down to here. Instead of being up here, we need to move this all the way down to here. And this is what our other machine at UKEA does. So this is called Mast Upgrade. It's much smaller than JET. You can see here, here's a person standing next to it, a person standing on top of it. So it's much smaller than JET, but it still produces very, very hot temperatures. So we can test out new systems, for dealing with these high heats and hot temperatures on this machine. And that's exactly what we're doing. It's got a few objectives. The first is to develop these novel, what we call exhaust concepts. The second is to develop new knowledge for ITER. And the third is to prove the feasibility of this different design. So what we've done here is we've pushed everything that makes a tokamak much closer to the center, so that it's a smaller, more compact, more efficient way of running a machine. And it's this top one, this novel exhaust concepts, that I'll talk about a bit more now. So how do you do that? Well, let's take the analogy of a car first. So in a car, you've got a hot engine. You want that heat to be nice and cold by the time it goes out of the exhaust pipe, so you don't melt all of the plastic or all of the metal work around the end of your car. So that's fine. But what happens if your car runs on fusion power and it's very, very, very hot here? If it's very, very, very hot here, then it's still very hot by the time it gets to the end, and you're going to do damage now. So what's the most obvious solution to sort this problem out? Well, the most obvious solution is you just make this exhaust pipe longer. The longer it is, the more time the gas has to cool, so that by the time it gets to the end of the exhaust, it's nice and cold. And that is essentially exactly what we've done in Mast Upgrade, but it's much more complicated in a tokamak. So this is what the inside of Mast Upgrade looks like. This is what the plasma looks like. And before Mast Upgrade, all of the heat would have been put down on a surface about here. So this is what we call the conventional case. It would have just been dumped on a surface here. But in Mast Upgrade, we've got this new chamber, which we call the Super X diverter. So in this chamber, we're now extending the space that we're extending the point where the heat goes and hits the material surface from here over to here. Now, that's not very far, right? That's only about half of a meter in space radially, but actually all the time, the plasma is looping around the machine. So the heat itself has to go about 30 more meters from here to here before it hits the surface. All the time it's traveling around there, it's losing energy as light, and so it cools. And so by the time it hits the surface, it's a lot colder than it was in this case. We did some modeling, so we did some numerical simulations, and we tried to predict this. And this is what our simulation showed, which was that in the Super X diverter, in this case, we should have about 10 times less power, less heat hitting a surface than we do in the conventional case. And when we ran experiments, this is what we found. So this is actual experimental data from Mast Upgrade when it started to run. And we found that we achieved this. So we got the heat in the Super X case right down here, 10 or more times lower than in the conventional case. This is a huge result, because up until this point, this was only theoretical, but this proves that this works. So if this works, this gives us a solution that we may well be able to scale up to a fusion power plant. And all of a sudden, this challenge that seems really big, really insurmountable, becomes something that we can solve. So that's really exciting. We've just finished our first experiments in this machine. The second experimental campaign is due to start in July 2022. So very exciting. And so how does that feed into, what do we actually do to design power plants? So there are lots of power plant design programs going on in the world now. Every single member state that's involved in ITER has a power plant design program. The UK's is called STEP. The EU's is called DEMO. China has one called the Chinese Fusion Experimental Test Reactor. Everyone has one. There's also a whole lot of companies in the private sector that are now creating these as well. And they've really boomed in the last 5 years. So the private sector has now raised £2 billion of investment to date, and it's still growing. In the last 5 years alone, there's been well over 15 companies formed to find different, novel, exciting approaches to fusion. The UK's design program, the one that we're involved with, is called STEP. So STEP takes this approach of what happens if you make everything much smaller, everything much more compact. Well, the first thing that happens is that you make the cost lower. So it's a cheaper way of getting diffusion. The goal of STEP is to produce predictable net electricity and to connect a power plant to the grid. It's on quite an ambitious timeline. So we're in this first tranche now. So from until 2024, we're developing the concept design for this, and we're selecting where it's going to go, and we're figuring out how we're going to get investment into it. From 2024 to 2032, we're detailing out the design. We're starting to buy big pieces of infrastructure with the goal of having the whole thing complete and putting connected to the grid by 2040. So it's a really ambitious timeline, really exciting. Oh, excuse me. So how can you get involved if you're interested? Well, the Mast Upgrade experimental campaign is starting again next year. There's all sorts of exciting stuff to do in theory and modeling around plasma instabilities, steady state plasma simulation, all sorts. The best thing you can do to get involved if you're interested is just talk to us. We're very open to collaboration. I think we have collaborators in Brazil, and we certainly have collaborators all over the globe. So we're very open to collaboration, and you're more than welcome to reach out to me, or I can put you in contact with any of my colleagues if you're interested in getting involved. And if you want to find out more, there's various websites here. I will stop talking now. You're more than welcome to connect with me on LinkedIn or anything else. I'd love to chat to you. I don't know if we've got time for questions or not. If we do, I'm more than happy to take any questions you've got. But again, I'm very sorry for running over my time. I hope that it was worth the wait at the start.
We certainly do. First of all, thank you very much for a great talk. Yeah, we have time for questions. Always, please raise your hand or just unmute yourself and speak. Yeah.
Or if you don't have any questions now, you're more than welcome to send them to me by email afterwards.
Actually, so I have a question, since we are, and for the people who are sort of in my field of research, which is core gluon plasma, I just want to say that this is obviously an applied project, but it led to some very important breakthroughs in sort of basic physics, namely plasma instabilities in the 60s. I mean, people actually thought this was easy. And then they discovered that plasmas are inherently unstable, and here we are. But the physical processes of this are still being researched, and also the analogy of this in QCD has been proposed as a thermalization mechanism for the matter which is produced in lead-lead collisions at the LHC, because we have this puzzle that things seem to thermalize really quickly, also in small systems. And regarding this, I mean, my question is there a definition of entropy for this, for the process that you have? And if so, is it like isentropic, or does entropy sensibly increases during the existence of the plasma?
Yeah, I mean, all of this is well, no, that's not true. I was about to say all of this we treat as thermalized. There are quite a lot of non-thermalized or non-local processes that go on in here, particularly actually. So what's really interesting about these plasmas is that they tend to be where you would think that they would deviate from being Boltzmann, from being thermalized, you know, where they would start to do isentropic or other interesting features. You'd imagine that would be right in the core, right, where it's hottest. But that's not the case, because what tends to happen is, because they're on closed field lines, although they are very non-collisional, they go around enough that they collide. They have enough collisions by the time they finish on their orbits that they thermalize. So actually, a lot of the sort of thermodynamic behavior of these plasmas in the core tends to be fairly benign. But in the edge, after you get out of that core bit, when you get into that scrape or flare, the bit that comes down and hits the material surface, all of a sudden you lose that mechanism by which they thermalize. So you have all sorts of non-local transport effects that start to come into play there, and then you have really a lot of interesting stuff. Now, I'm afraid we don't really study the sort of thermalization or entropy effects in our plasmas very much, because it's either very much a thermalized Boltzmann plasma, or it's too complicated for us to figure out what's going on. But yeah, there's certainly a lot of distribution functions in here that are non-Boltzmann. Of course, we have stuff like all of the features of Landau damping and instabilities that you get from bump on tail instabilities from complex things in distribution function, that sort of thing as well. We get what's quite interesting in these plasmas is you have a population of very high energy fast ions as well, and they do all sorts of interesting instabilities, fast ion instabilities, because of their interaction with the core distribution function and then their own various mechanisms that go on in their own distribution function. So there's all sorts of really interesting stuff that goes on there as well. I suspect that you could probably tell me better than I can tell you actually, but I suspect that the relationship between the sort of work you do with thermalization in quark gluon plasmas. Interestingly, I was actually talking to one of my colleagues about this just last week. His wife works on Atlas. So he's got links in with the LHC, and he works on Mast Upgrade. In fact, he leads Mast Upgrade. I suspect that's closer to the sort of stuff they do in inertial confinement, right? Because that's those plasmas thermalize, but they thermalize on ridiculously fast timescales because of fast electron motion. So I suspect it's closer to that, and I'm afraid I'm a little bit less clued in on that area of physics. But yeah, I think there are a lot of overlaps. Yeah, what's really nice about this area is it's produced two things. It's produced a lot of very fundamental understandings in how plasmas work. We have this theory of gyrokinetics, which probably doesn't apply to your area because it's about magnetized plasmas, but gyrokinetics came out of fusion research. Lots of instability works, some really fundamental stuff just about plasma self-organization. But also we've got a lot of really industrially applied stuff that's spun out as well. So robotics, some of the robots that we have used in fusion for 20, 30 years, the sensor technology on those robots now gets used in autonomous cars, self-driving cars. So it's a really, it's like the space shuttle program where you develop really fundamental understandings, but also these sort of spin out stuff. I've always found myself in between both. So I've never been a fundamental theorist, but I've always been sort of reasonably close to the fundamental physics. I should have said my background is in turbulence, so I've always done a lot in turbulence.
It's as fundamental as it gets.
Oh yeah,
yeah. Heisenberg say. Leonardo, you had a question.
Can you hear me?
Yep.
Yes.
Oh, yeah. So I'm gonna turn on the camera just a second. Oh, here. All right.
Hi, nice.
So yeah, I had a question actually. Is the plasma on for short bursts of time, or does it, or are actually either in these other reactors trying to have maintain a plasma for long stretches of time?
Yeah,
like a constant plasma for long stretches of time.
Great question. So I'll answer that in two parts. First off, so I said that there are these different concepts of fusion, right? There's inertial, at one extreme, you've got inertial confinement fusion, which happens very, very fast, so nanoseconds. So to make a power plant out of that, you have to have one of those nanosecond bursts going off. I think you have to have about 60 a second to be able to make usable electricity out of that. So that's what they're trying to do. They're at the moment, they're about 1 an hour. So there's a bit of space to go there. In Tokamak, so my area, the thermalization time, so the time it takes the distribution function to relax and everything to essentially go to an equilibrium, is on the order of about 100 milliseconds. So if you can operate for, I don't know, a second, you're essentially in steady state, which means that whether you operate for a second, 5 seconds, 10 seconds, 100 seconds, it's all about, from a physics point of view, the physics you're testing is basically the same, which is why on today's machines, we run for between a second and 10 seconds. So jet typically runs for about 10 or 20 seconds. Mast Upgrade typically runs for about 1 or 2 seconds. And that's just because these are just testing physics. But actually producing power, so ITER, when it produces its 10 times power output that you put in. Uture will run for 400 seconds, so it will run longer, and it's because it's going to use superconductors as opposed to copper magnetic fields coils, which is what we use today. And a power plant, we hope, will either run continuously or for half a day at a time, turn off for an hour, run for another half day, something like that. So there are various. There's a real challenge though to running continuously. So you can imagine a pulse. Exactly. The real challenge we have, right, is at the center of this machine, you've got a solenoid. So in order to induce a current, in fact, I've got one behind me, look. So at the center of this machine, I've got a solenoid, and that induces a current that goes around the machine. To induce a current, you have to create an EMF, so an electromotive force. The way you do that is you take a power supply and you swing it from minus some very big voltage to plus some very big voltage, but you can't do that for infinity. So you fundamentally, a machine like this, you fundamentally cannot run steady state. So we have to come up with clever ways where you can start up the machine like this, but then you take other methods take over, which means you can turn off the central solenoid and you keep it running. And that's a big area of research. So it's something we can't do today, but we have ideas about how we're going to do it in a power plant. So it's every single question you ask about fusion science is like this, right? You think you've asked a question which is quite a sort of simple question to ask, but it's so hard to do that there's always some really challenging aspect of engineering or science behind it. But to answer your question simply, yes, a power plant will hopefully run either continuously or in long pulses.
Okay, thank you very much, Nick.
Thank you.
That's it.
Sorry, more questions? I guess I have one. So, which will date me. So cold fusion has definitely been discredited, right? Muonic and sort of crazier alternatives. That's not going to happen.
Yeah, they like muonic catalysis, I think they called it, the 1980s one. Yeah, I think so. I haven't heard anything more about it. None of the. I always think that the best indicator you can get is what private companies are willing to invest in. And none of the fusion companies that are in existence at the moment are cold fusion companies. All of them are hot fusion. So I think it's reasonably safe to say that cold fusion has died a death. I hope it stays there. Interestingly, I always tell people, so you're the one community that will probably be angry at me for this, because I always tell people that jet is the hottest place in the solar system when it runs. But of course, quark gluon plasmas get to like tera electron volts, don't they, or something ridiculous? Sure. Yeah.
So temperature, our temperature is an MEV. Yeah.
MEV. Yeah, there you go.
Hundreds of MEV.
Hundreds of MEV. So it's not technically true, but of course, jet runs for a sort of longer sustained period. So,
of course. Okay, more. I guess I have again another follow-up question. The stage of converting the plasma into electricity. I guess this wasn't one of the parts of that you've mentioned, but that must be that you've sort of concentrated on. But that must be really inefficient.
Yeah.
Or is there something clever that is being?
There is some. So the main approach is the same as any other power station at the moment. So it's just steam turbine, and what's a steam turbine? I think maximum efficiency is like 63% or something. So so you lose efficiency there. You also lose efficiency in the heating system. So the heating systems we use are only 70% efficient by the time you're putting heat into the plasma, and then only about I think it's like 60% of that heat actually gets absorbed. So there's quite a lot of inefficiencies in the process. It's the best we can do, but there are a lot of inefficiencies in the process. One of the things that we're looking at for STEP is a different heating system. So a heating system which is almost 100% absorbed into the plasma, and is like 95% power efficient. So that would be great. That's using microwaves to heat the system. One of the private fusion companies that recently got a lot of funding is exploring a different way of harnessing power. So they're exploring a concept which takes a plasma, a hot burning plasma, squeezes it, and then the fusion happens and it expands. And they are trying to use that change in magnetic flux from the expansion and contraction of the plasma to induce, to essentially drive a transformer and create power that way. It sounds great. They are some way off proving that technology, but it's a very exciting idea. I don't think it's an idea that a public program should follow, because it's not a really very sensible way to spend taxpayers' money. But it's it's a really exciting idea. So yeah, we're sort of riddled with the same old inefficiencies that any other power plant is riddled with. But hopefully, what I always say is let's get electricity first. Let's get to electricity produced, and then figure out how to make it better. Because there's so much that can go wrong just to get the prototype. Let's get the prototype, and then let's make it more efficient.
Further questions? If not, thank you very, very, very much. This was actually a really great talk, exactly the level that I was hoping. And yeah, we're hoping you guys will succeed. We really are.
Oh, thank you very much. It was very interesting.
Well, you're very welcome.
I'm a big fan of fusion.
Excellent. We'll keep looking at the news lines, because there's exciting stuff. Do you want me to send over my slides somehow, or Giorgio?
Yes. I'll send you. Let me stop the recording.